What is going on, guys? Hope you're doing freaking awesome. So in this video, we're going to learn about mean average precision. So more precisely, our goal in this video is to understand and implement the most common metric, which is mean average precision, that is used in deep learning to evaluate object detection models. And concretely, after watching this video, if we read something like mAP at 0.5 and then 0.05 and then 0.95 in a research paper, our goal is to understand exactly what that means and also how we can do similar type of evaluation on our own model. So the first step in mean average precision is to get all of the bounding box prediction on our test set. So let's say our test set just includes 3 images, and in this case, the green ones are the target bounding boxes, and the red ones are the predicted bounding boxes that are outputted from our model. And so for each outputted bounding box, for the red ones, as you can see, there's a score associated with that bounding box. So I've mentioned this briefly in previous videos, but the outputted probability or the score for the bounding box is the probability that the bounding box believes that there's an object in the outputted bounding box. So again, the red ones here are the predictions and the green ones are the target. So let's take a look at just the first image. And let's see if we can look at just the predicted bounding boxes. So we have 3 bounding boxes with different confidence scores, 0.3, 0.6, and 0.7. And so if we want to evaluate just if each of those bounding boxes is a true positive or a false positive, then we would get that looking at the first one for the 0.3 confidence score, then it does not share an IOU with any target bounding box that's greater than 0.5. And so that means that that bounding box is a false positive. And if we look at the 0.6 confidence score, we see that it seems to detect some part of the dog, but it's not having an IOU that's greater than 0.5. So that's still a false positive. Although if we look at the one with 0.7 confidence score, then that one does share an IOU with the target bounding box that's greater than 0.5. So we say that that's a true positive bounding box. For image 2, we only have 1 prediction, and that's a true positive. For image 3, we can see that we have 2 bounding boxes at the top, those are both false positives. And then we have an 0.9 confidence score bounding box that has a pretty high IOU, that's greater than 0.5, with the target bounding box, so that's a true positive. All right, so if we just summarize all of those bounding boxes into a single table, this is what it would look like. Then for the next step, we want to sort this table by descending confidence score. So then the resulting table is going to look something like this. For the next step in mean average precision, we're going to first have to understand 2 key, very important metrics, which are precision and recall. So just a summarization so far, we've looked at true positives and false positives. So true positives are the bounding box prediction that share an IOU greater than 0.5 with a target bounding box. And the false positives are those that doesn't. So those are, incorrect bounding box predictions. In this case, false negatives means that we didn't output a bounding box for a target bounding box. And true negatives, we don't really have in this context, because that would mean that we didn't output a bounding box that weren't there. So that in this case, true negatives is not something to consider for the case of bounding box predictions. All right, so for the first key metric, which is precision, we take the true positives and we divide that by the true positives addition with the false positives. So, essentially in words, that is, of all the bounding box predictions that we made, what fraction was actually correct. For the second key metric, which is recall, we look at the true positives and we divide that with the true positives added with the false negatives. So we essentially divide by just the total number of target bounding boxes. And the numerator is just the number of correct bounding boxes that we predicted. So in words, this means of all of the target bounding boxes, what fraction did we correctly detect? And so as you can see, these are 2 very different metrics. And there's sort of a battle between this precision and recall. And different applications may prioritize recalls, recall, and others might prioritize precision. So let's just take self-driving car as an example. In that application, they probably prioritize not missing any pedestrian. So that would mean that they value having a high recall. All right, for the third step, we want to calculate the precision and the recall as we go through all of our output bounding boxes that we have predicted. And this is from the table from the second step where we have sorted this by descending confidence scores. So for the first one, we have that's a true positive. So the precision for so far is going to be 1 out of 1. Our predictions so far have been 100% accurate. And for the recall, we've covered 1 out of 4 total bounding boxes. For the second bounding box prediction, we have that it's a false positive. That means that the precision is going to be 1 out of 2, and the recall is going to stay the same because we haven't covered any more of the target bounding boxes. And for the third bounding box prediction, we see that it's a true positive. So we're going to up the precision by 1, meaning it's going to go to 2/3, and the recall also is going to be up by 1. So the same logic on the rest of these bounding box predictions. These are the numbers that we're going to get. So we're then going to take these values, the precision and recall, and we're going to plot the precision recall graph. So if we do that, where the precision is on the y-axis and recall is on the x-axis, this is the resulting graph from those numbers. The idea behind average precision is then that we're going to take the area under that graph, and that in this case is going to be the average precision for the class dog. So if we calculate that area, it's going to be approximately 0.533. But this was only for the dog class, and we actually need to do this for all classes. So let's say we do this for cats and dogs, then and if we just say that the cat AP is going to be 0.74 and the dog AP, which we just calculated, was 0.533, then the mean average precision is going to be those two added together and divide by 2. So that was a lot, but are we done yet? And unfortunately, we are not. So we have one more additional step. All of this was actually calculated given a very specific IOU threshold. In this case, I've mentioned the IOU threshold of 0.5, but we need to redo all of the computations for many different IOUs. So for example, we might want to do this the mAP for IOU 0.5, 0.55, 0.6, and then up to 0.95. So, and then we average all of these mean average precisions, and this will be our final result. And this is what is meant by writing mAP at 0.5 with a step size of 0.05 up to 0.95. All right, so let's try to now implement this from scratch in PyTorch to make sure that we really understand and get all of the details behind mean average precision. So what we're going to do first, we're going to import torch. We're going to do from collections, import counter. We're going to use that later on. And then from IOU, we're going to import intersection over union. So make sure you have the IOU implementation from our previous video, and then we're going to import that, and we're going to use that in our mean average precision. So let's define mean average precision. So the first thing we're going to send into our mean average precision is some prediction boxes, and these are going to be all of the prediction boxes across all training examples of our entire training test set. Then we're going to have some true boxes, and again, those are all the true bounding boxes. We're going to set some IOU threshold. Let's set it to default of 0.5. We're going to specify some box format, and this is from the IOU implementation, depending on if you have corners or midpoint or whatever. We're just going to specify this to be corners by default, and then num class we're going to set to 20. And then we're going to do... All right, so we're going to start with having average precisions to be a empty list, and we're going to add the average precision for each class in that list. So by the way, why I'm setting num classes to 20 by default here, because that is what the data set we're going to build for YOLO has. So I'm just setting that as default. All right, so we're also going to set some epsilon to be 1e minus 6. We're going to use that later on for just numerical stability. So the first thing we're going to do is we're going to do for C in range of num classes. And this is kind of what I mentioned previously, in that we need to calculate it for each respective class. But before I move on, actually, let's talk a little bit about the input. So the pred boxes is going to be a list. So there's going to be a list, and it's going to be a list with all the bounding box predictions. So here we have 3 bounding box predictions, and all of them is going to have its first as the train index. So what is the image that these bounding boxes, or rather this bounding box, comes from? Then we're going to have the class prediction for that bounding box. We're going to have the probability score, and then we're going to have x1, y1, x2, y2, and similar for the sort of for the others here. All right, so that is just one bounding box, but it's important to know how these are structured, and this is in a similar, and this is similarly for the true boxes, but these are just containing a list of all the true boxes for each of the images. Okay, so moving on to our classes, we're gonna set detections to an empty list. We're gonna set ground truths to an empty list, and this is going to be for a particular class C. So we're gonna go through for detection in pred boxes. So we're gonna go through all of the predictions. We're gonna check if the detection of index 1, remember that's a class prediction, if it's equal to the class we're currently looking at, then we're gonna detections.append that detection. Then we're gonna do pretty much the same thing for true box in true boxes. We're gonna do if true box of index 1 is equal to C, then we're gonna add that to ground truth. So we're gonna ground truths append true box. All right, then we're gonna check, we're gonna do amount of the bounding boxes. That's what I'm gonna call it. I'm gonna do counter of ground truth of 0 for ground truth in ground truth. So let me explain what this is going to do. So remember that the first index is going to be the training index. So let's say that we have image 0, and that has 3 bounding boxes, and image 1 has, I don't know, 5 bounding boxes. Then when we're using this counter, it's going to actually count how many it has, and it's going to create a dictionary out of that. So the result here is that amount bounding boxes is going to be a dictionary with 0 as key, and then value 3, and then key 1, value 5. And that is because image 0 has 3 bounding boxes and image 1 has 5 bounding boxes. If you're a little bit confused over this, then I encourage you to just read a little bit on the counter. All right, the next step is that we're going to do for key comma val in amount bounding boxes dot items. And we're going to do amount bounding boxes of key. So that's 0 and 1 in our example. We're going to do equals torch dot zeros of val. So instead of having just 3 right here, we're going to create a tensor of that has 3 elements of zeros. So, you know, after this, after doing that, amount bounding boxes will be 0, and then torch tensor of, you know, 0, 0, 0, and then 1, and torch tensor of 0, 0, 0, 0, 0. So it has 5 zeros, and that will be the sort of the updated one. So that's all we're doing for those lines. And I better explain why we're even doing this, right? So why we're doing this step right here is because, so we need to keep track of the target bounding boxes that we have covered so far. So we can't have, you know, multiple prediction bounding boxes for one target bounding box and count them all as correct. Only the first one that covers a target bounding box is correct, and the other ones would be false positives. So this is for keeping track of the ones, the target bounding boxes for a particular image that we have taken or covered so far. Next step we're going to do is detections.sort key equals lambda x and then x of 2 and then reverse equals true. So this is for sorting over the probability scores. Then we're going to do true positives. We're going to do torch.zeros of the length of our detections for this particular class. And then let's see. And then false positives is going to be torch.zeros of length of detections as well. And then the total true bounding boxes is just equal to the length of the ground truths. All right, so now what we're going to do is we're going to go through for detection. We're going to go through all of our detections in this particular class. We're going to do for detection index, comma detection, in enumerate of detections. All right, so now we've taken out a particular bounding box for a particular class. Then we're going to do ground truth image is bounding box for bounding box in ground truths if bounding box of 0 is equal to detection of 0. So what we're doing here is we're only taking out the ground truths that that has the same index as as our detected bounding box has. We only want to compare bounding boxes for a single image. We can't compare them across different training examples, different training images. So that's what we're doing in this right here. Then we're going to do the num ground truth is equal to the length of ground truth image. So that's the number of the number of target bounding boxes in this image. All right, then we're going to keep track of the best IOU. So we're going to do for index, comma, ground truth in enumerate ground truth image. So we're going through all of the bounding box, the ground truth bounding boxes for this image. And here is when we're actually going to use the IOU. So we're going to use intersection over union. We're going to send in torch.tensor of detection. And we're going to send in 3 and forward. And this is because the first one, let's see, what was it actually? So the first one was training index and then class prediction and probability score. So we only want to take these 4s for the actual IOU, right? So that's what we're doing there. And then we're going to do the same thing for the ground truth, GT, and then 3 and forward. I'm going to set the box format to be box format. And we're going to close that function call. Now we're going to check if the IOU is actually greater than some best IOU so far. We're going to update our best IOU to be this IOU. And we're going to do the best ground truth index is equal to index. And this is going to be sort of the index from right here in this ground truth image. All right, so when we've done all of that, we have taken out a single bounding box for a particular class in a particular image, and we've taken out all of the ground truth bounding boxes for that particular image. Now we've compared that bounding box between all of the target bounding boxes, and we've checked the IOU between all of them, and we've kept track of the best IOU. Then we want to check if the best IOU is greater than our IOU threshold. That means that this prediction was correct, right? But not necessarily. We need to also check that we haven't covered this bounding box before. And that's when this counter thing we did comes into play. So we're going to do if amount of bounding boxes of detection of 0, that's the training index of our current bounding box prediction. And then we're going to get the index of the best ground truth index, right? That's the one, the target bounding box index. And that is equal to 0 because it's initialized at 0. That means that this target bounding box has not yet been covered. So we're then going to do, this is counted then as a true positive. So we're going to do true positive of detection index. We're going to set this to 1 because because this detection that we just did, which has index of detection index, this is a true positive. So we're going to set this to 1. We're going to do amount bounding boxes of detection of 0. And then we're going to do best ground truth index. And we're going to set this to 1. And why we're setting this to 1 is because now we have covered this bounding box. This target bounding box is now covered, and we don't want to cover it in the future. So we're going to do amount, or rather, if this is not the case, so else, we're going to do false positive of this detection index, right? This means that this was not a true positive, and because there was no IOU over this threshold. All right, and then also if this else is if this bounding box was already covered previously. And this else right here is if the IOU was not greater than that threshold. Then we're also going to set that to a false positive. All right, next up is we're going to do the true positive cumulative sum. And we're going to do that by torch.cumulative sum of TP and dimension equals 0. So what this is going to do is essentially when we calculate the precision and recall, that's what this is going to be used for. So essentially what this is going to be used for is that, as you saw in the example previously, we continually added as we got a correct or incorrect prediction. So so this is for the precision and recall. Essentially what cumulative sum does is that, let's say we have 1, 1, 0, 1, 0, something like that. This means that this was correct, this was correct, this was not correct, this was correct, and this was not correct. Cumulative sum is going to be that we add them what they have sort of got to so far. So here we have 1. If we add all of the ones up to including this point, this is going to be 2. This is still going to be 2 when we have 0. And then with the next one, we're going to have 3 and then 3. So I hope you get the point here. Hopefully, if you don't understand this, you can read up a little bit more on cumulative sum. And we're going to do the same thing for false positive. So torch.cumulative sum, false positive, dimension equals 0. And then we're going to, now that we have those two, we can calculate the recall and the precision. So recalls is going to be the true positive cumulative sum divided by the total true bounding boxes added with some epsilon for the numerical stability. The precisions is going to be torch.divide true positive cumulative sum and true positive cumulative sum with false positive cumulative sum and epsilon. And I can't really remember why I used torch divide here. It might be possible to just do normal division here. But yeah, so this is essentially here anyways, we're just dividing true positive cumulative sum divided by true positive cumulative sum and then false positive cumulative sum. And we're doing it element-wise. Then what we're going to do is we're going to do one more thing, which is important. So we're going to do torch.concatenate torch.tensor of 1 and precisions. So we need to add a 1 to the precisions because we want to start at the point 0, 1. If you remember for the example, when we calculated the area, we didn't have a point for 0, 1. For 0, 1. But we need to have that when we're doing numerical integration. So this is why we're adding this. So we're going to do the same thing for recalls, but instead of doing 1, we're going to do torch.tensor of 0, because remember precision is the y-axis and the recalls is the x-axis. And then we're going to add that to recalls. And now we can actually do the average precision. So average precision dot append torch.traps. This is the trapezoidal rule for numerical integration so that we get the area under those precision recalls points. So we're going to here send in the precisions, and then recalls. So this is a little bit weird perhaps, but this function torch.traps takes in y comma x. So these are the y values, recalls is the x values. All right, and then we're doing that for every class. Remember, this is still inside that for loop. Then after this thing right there, we're going to return the sum of the average precisions divided by the length of the average precisions. Now, is this enough, or are we done here? Not actually. So what we've implemented here is just for a single IOU threshold. So what you would need to do to calculate the example that I gave for different IOUs, is that you would call this function for multiple IOUs, store those in a list, and then take the average. But I'm just doing this implementation for a single IOU and not doing it that way. And that would be done outside of the function. All right, so let's see that this actually works. So we're gonna do conda activate deep learning. We're gonna do Python map test, and it ran 4 tests, and we actually got that correct on the first try. Has that ever happened in a video? I don't think so. This is a special day indeed. So, hopefully this implementation was clear. This is definitely not the most efficient implementation, and I did not spend much time on making sure that this is the best and most efficient implementation, because this is only going to be run once on actually evaluating our model. But if you do have any suggestions on improving this, then please do share it, because I'm always looking to make the code more clear, more efficient, and just better overall. With that said, thank you so much for watching the video. I hope you're following along with this video so far in object detection, because the next one is going to be YOLO from scratch, and that's going to be a long video, and we've done some work now to prepare for that in understanding these metrics, very important metrics. But anyways, I think I said thank you for watching. Thank you so much for watching the video, and I hope to see you in the next video.